Imagine walking into a bank, taking $1 billion, and leaving without a single camera or guard ever detecting your presence. Achieving this level of stealth requires the precise manipulation of light paths. To understand how to hide an object, we have to look at the mechanics of sight. Light sources emit photons that strike a surface and reflect outward toward your eyes. Your brain then reconstructs those intercepted photons into the images we perceive as reality. Visibility relies entirely on these reflections. Invisibility, therefore, is achieved by preventing any light from bouncing off an object and reaching an observer, transforming a visual illusion into a problem of applied optics. In nature, materials like glass and water allow light to pass through with minimal interference. The human body, however, is a dense physical barrier. We are composed of billions of cells filled with proteins, fats, and minerals. Our bones and organs create a complex, opaque internal structure. Instead of allowing light to pass through, these biological layers cause incoming photons to be absorbed, bent, and scattered in every direction. Skin alone reflects enough light to make a person visible from hundreds of meters away. Even if our tissues could become perfectly transparent, a biological observer would be blind. A retina must absorb light to form an image. If light passes through the eye without being captured, it cannot trigger the signals needed for sight. This creates a permanent trade-off. To be truly unseen by nature's design is to lose the ability to see. Because our biology is fixed, researchers are looking towards engineering to find a way around the physics of reflection. Consider how water moves in a stream. When it encounters a smooth rock, the flow splits, curves around the obstacle, and perfectly rejoins on the other side. An invisibility cloak uses this same principle. It is designed to guide incoming light around an object so that it continues on its original path, as if the object were never there. This requires the use of metamaterials, synthetic structures engineered at the microscopic level. These artificial patterns force electromagnetic waves to curve smoothly around a central void. While experimental cloaks can hide tiny objects from specific frequencies, bending the entire visible spectrum around a moving human presents a massive technical challenge. Metamaterials have turned invisibility from a biological dead end into a problem of material science. Beyond bending light, another path exists through active camouflage. This method uses a network of cameras to record the environment immediately behind a subject. Wearable displays or flexible screens then project that background onto the front of the clothing, creating the illusion of transparency from specific angles. Current research involves using AI to adjust these projections in real time, allowing the camouflage to adapt as the lighting or environment changes. Future concepts suggest a more advanced version, a suit composed of billions of nanobots, each detecting and redirecting photons to maintain the illusion from every direction. These systems prioritize the deception of the observer's eye, using active technology to hide what physics would otherwise reveal. Moving these concepts from a laboratory into the real world requires solving a series of compounding technical hurdles. A functional system must calculate light arriving from multiple directions, account for every color wavelength, and compensate for the heat and movement of the human inside. Because humans perceive depth and motion so acutely, even a slight delay in these calculations would cause the background to distort, instantly revealing the hidden person. While quantum physics is often cited in fiction, quantum optics currently only hides microscopic objects from specific waves. It provides no mechanism for a human to vanish from ordinary visible light. These environmental and physical variables keep the invisibility cloak among the most difficult challenges in optical physics. If these engineering challenges are eventually overcome, the impact would reach far beyond the laboratory. Surgeries could be performed with tools that don't block a doctor's view, and researchers could study wildlife without the presence of a human observer altering animal behavior. However, if this technology moves from specialized military use into the public sphere, the traditional boundaries of privacy would shift. Physical barriers like walls, gates, and visual distance lose their function when a presence can no longer be detected by the human eye. Security protocols and law enforcement rely on the ability to monitor movement. Without that visual data, current methods of maintaining public safety become obsolete. Like any tool that grants significant leverage over the environment, the ability to control light carries a weight of responsibility, requiring a rewrite of the laws governing our interactions. We have moved from the myth of disappearing to the science of light manipulation. The question is no longer if we can trick the eye, but how we will live in a world where the seen can become the unseen.